Welcome everyone to the class. Now let's see how it is done in popular culture, right? So people don't see a CNN as a regularized MLP. Okay, they start by writing an image. Let's do that. So let's say that we have this grid kind of topology. Let's say that it is P cross Q pixels, and please note that this P times Q is what our D is, the data dimension is. Okay. Now this is we work with this sort of a topology. This is your question. We work with this sort of a topology. Now what is the operation that a neuron does? We know that it's inner product. Okay. Typically in an MLP, the weights of a particular neuron is represented as what is called as a kernel or a filter. Because I lifted the pen. So this is it's mostly made symmetric. So it is let's say k by k, and this is so W1, W2, W3, W4, W5, W9. I mean it's not. I'm just assuming that it's a 3 by 3 the kernel, right? For example. So yeah, this is how it is. Now, what is the operation that we do in an MLP when we are computing the neuron is sigma W transpose X. This is the operation that we do, isn't it? So what is that in terms of this kind of, if you just want to mimic that in this kind of a topology, what we do is take this, maybe I should have written a different color to, this is k by k, place this k by k here and do an inner product. That's it. That's your W transpose X. And now you see why it's local receptive field. So if I take this image and do a roster can and make it a d-dimensional vector, doing an inner product with a k by k symmetric so-called filter is equivalent to doing this particular operation, right? The W transpose X. It's exactly the same thing. You see that? Yeah. Now what I do is I slide this filter. So let's say that I am doing in a non-overlapping way. I slide this filter k pixels. Okay, by the way, every data dimension is called pixel in the image processing community. Okay. So now I slide it by k and do the same operation and keep doing it and keep moving this filter in the right direction and left, then do this, right? Then what am I doing? I'm incorporating both the regularizers, isn't it? The local receptive field and parameter sharing. Your question is answered now? So now, yeah, so now you know, right? I mean, we are not representing it as a vector, we are just striding it, okay? Is this all right? Do you see that doing this operation is exactly the same operation that we did on MLP? And by the way, inner products, okay, are called convolutions in the signal processing community. Of course, you need to flip one of the, I mean, if you have two signals, right, or two vectors, take one vector, flip the other, and then take a inner product is what is called as convolution. I mean, of course, you need to slide that filter over the input signal. That's exactly what we are doing here. I keep saying convolutional network is a bit of misnomer because you are not flipping. This should have been correlated neural network or something. It doesn't matter, but you got the idea, right? The convolution operation, everybody, I'm assuming that everybody knows what convolution operation is. In signal processing community, if you are given two vectors, one is called the signal, the other is called the filter. You stride that filter over the signal one stride at a time and take the inner product and add. Whatever you get is what is called as convolution product. So this operation that we are doing, so an MLP with a feed forward operation with parameter sharing and local receptive field is the definition of convolution. Isn't it? That's a hyperparameter again. You can shift one pixel, you can shift 3 pixels, you can shift k pixels, doesn't matter. That's called stride size. That's a hyperparameter. You got it? Inner products with local receptive field and parameter sharing is nothing but convolution. Do you all see why it is the case? Okay, so that's why the name. So that's why you say that you do this convolutional operation here. This is the conv operation, and what will you get? You get few more neurons, right? So every inner product that we take, okay, well, we have to do conv, and also we'll have to do this nonlinearity operation, otherwise it becomes a linear filter, right? It's a neural network after all, unless we have this nonlinearity, we will not have universal approximation theorem working, so we need sigmoids. So do the convolution and then pass it through a sigmoid pixel wise, and you get a few neurons, and those neurons are again arranged as a grid. So each of the pixel here is the outcome of uh, one convolution, right? Or not, I mean the entire thing is called convolution. So you take the filter, place it on one subset of data, do an inner product, pass it through sigma, is what you get. I mean is what gives you the one activation map. It's also called activation map or a pixel in the second layer. So what will be the size of this? If this is, you start with p by q, what will be the size of the second activation map? Yeah, it will be p by k, q by k. The yeah, the floor of it. If I am assuming that the stride is k, if I make it stride dependent, this size will also be stride dependent. Do you see that? That's a hyperparameter. Typically stride sizes, if filter size is taken to be 3 by 3, stride is taken to be 1 by 1 and so on, and you will have to also ensure that the sizes of these things match by doing what is called as zero padding, which is if the stride and k are not matching, right? So what happens is if you take 3 by 3, the last operation will only have 2 pixels, you need 3 more, so you have add 0 to the final layer and then continue doing that. That's called padding. Okay, the size of the next activation map depends upon the size of the filter, okay, and the size of the stride choice and the padding that we do. I think it's clear. Is this all right? Do you see this as an MLP now? This is an MLP with these two regularizers put on, right? Any questions now? In MLP we neither do local receptive field nor we do parameter sharing, right? Of course, I mean even parameter sharing is understood as same. These things are taking the same value with probability 1, no? Correct. See now, if you see the weights corresponding to this neuron as 100 dimensional, then some of the dimensions are probability of some of the dimensions of the weights are 0. Probability of the other dimensions are taken to be exactly the same thing, conditioned on these the weights of the other neuron. That's also a strong regularizer, right? So this is the story, right? MLP with parameter sharing and local receptive field becomes a convolutional operation, and that's what a CNN is. So one of the rules of the game is that don't ask questions that have not, don't use terms, rather the ones which I have not used in the course. I'll talk about it in a while. Yeah. Any questions on this? Yeah.
So, sir, does this mean we can treat the elements of a matrix as a specific neuron?
Which matrix?
The P by K cross Q by K matrix. So
this one.
Yes.
This is the outcome of a neuron, right? See.
Yeah, that value, right?
Here, yeah, there is an implicit neuron, and the output of this is what this thing is.
Okay. Do we expect sort of fewer and fewer neurons in the subsequent layers?
That's an architectural choice. You are not there in the previous class, I suppose. Is it? Okay. Then I told you, right, in the typically for classification problems, when you go deeper and deeper, the number of neurons keeps decreasing because the input dimension is much higher than the output dimension. Yeah. Is it? Oh, this should be the stride. The denominator should be stride. So this is P. Yeah. So Q minus, correct. P minus K plus 1, Q minus K plus 1 divided by S, where S is the stride size. Yeah. Okay. Fine. It's simply k, there is no 1 because we have not padded also. Yeah, fine. Okay, fine. Okay, the story doesn't stop here, right? So I told you there is one other aspect to it. There was another question that he asked. Isn't it restrictive that if you do this, this one orange k by k filter is only doing one particular type of feature extraction, right? Whatever feature it extracts. Is it a good idea to do? It's not. So what we do, what is done typically is that you have another filter. And do the same operation again. It would have been good if I had used orange here. So another p minus k, q minus k thing, and let's call this k. Okay, hold on. This is k1, this is k2, so what happens is that you take the exact same input image or input data point and do this now. One second. There is another convolution here, and after that we still have this operation. What? Q minus k plus 1, is it? Okay, fine, if it's there, okay, depending upon the padding. So what are we doing here is that we take maybe let me just make this also orange color. I think it's better that way. Okay, yeah, I think now color coding is also correct. The image is black and filters are different colors and activation maps different. Is it? So what is done is that you use another set of filters, right, to and do the exact same operation. So now this can learn a different feature. Does it make sense? Now from an MLP standpoint, what are we doing? It can be K2. So I'm using K1 and K2 just to indicate that these two are different filters. In fact, they can also be of different sizes. It's okay, doesn't matter. Just this is just to ensure that there are two different filters, right? So now from an MLP standpoint, what are we doing? It is not this direction that I'm talking about now. I'm talking about another direction which I cannot represent on as plane. Right? So there are other set of neurons that are coming out of this thing, right? Yeah, you see this stack of neurons in the other. Actually, it's a dimension now. Yeah, multiple filters for, and every of this filter or every of this filter will be shared across different data dimensions, and there will be parameter sharing. You see what I'm saying? Now, how is it done? Is that, I mean, typically it is represented by stacking all these outcomes, right? One before the other. So you create tensors. You understand? Now, how many filters can we have in each layer is another hyperparameter. Do you get it? Right? So each of the filters will now learn different parameters, different features. The hope is that they learn different features. There is no guarantee because still we are throwing it to ERM's mercy. That's why you have 70 billion parameters. That's why CNNs and ResNets and all that have those many parameters, because this is how it is designed. Is this clear to all of you? See, Chandan made a nice point. He said that you will have to have the dimensions of these two filters to be the same, otherwise the dimensions of the outcomes will not be the same, which will not enable you to stack them one below the other, right? Which is the point, which is a correct point. That is how you do it, unless every time you do filtering you will have to pad it with a different size so that the outcome will have the same dimensions. But I used K1 and K2 just to ensure that there are two different set of parameters. Now to your question, when we are doing backprop and forward pass, right, we'll have to ensure that these things are encoded. Can be done, which can be done, right? Is this clear? So let's now have a unified view of all this. So a CNN is defined this way. So generally start with a data which has so you have P by Q by R. Data itself can be a tensor of dimensions P by Q by R. This is a grid. What is an example? A color image. Color image has 3 channels. So this is the third dimension is called channels in the computer vision language. And I'll come back to the MLP view here, because as I said, it's easier to look into that way. So all of this can be stacked into a large d-dimensional vector where d is P times Q times R. Remember that. It's just rearrangement of data in a particular way. So an RGB image, okay, that we see on our phones and computers have P by Q by 3 pixels. If you go to the electronics, right, what actually happens is there will be a sensor and there will be a grid of sensors, and each pixel is actually a physical sensor. If you have 408, 4086 or 4086 as your image size, there will be those many sensors in your camera. Every pixel is a physical sensor. On top of it, they would put something called a Bayer pattern, which are filters, which are physical optical filters that would block some wavelengths and only let some other wavelengths to pass. That's how you get these 3 channels RGB. I don't know if you have actually seen an R channel. It looks like a grayscale image to human eye. You have to reverse that base pattern while rendering. Those are, again, I am not here to teach computer vision, but anyway, so this is how you get 3 channels. This is one possibility. The other possibility is that suppose you are looking at an MRI. Every slice of an MRI, right, is one channel of the image. So this will have P by Q by 1000 channels. So it's a tensor. Okay. So if you see what is called as a tomography, I think, right, where you take different slices of X-rays and then stack them as a channel. Even video, a video frame is this, right, stacking of multiple static channels, and where the third dimension is the temporal dimension. So a video can be seen this way. The most generalized version is that you have a tensor of size P by Q by R. You can add one more dimension, it doesn't matter. That's a tensor. Is that okay? Now, so start with the P by Q by R data. Huh? Why? I thought my P was capital here. That's the first letter of my name. That can't be small. Okay. Yeah. Anyway. Right. So now what happens is that you now have filters, right? You have filters. And now if you have the generalized P by Q by R as your input data tensor, okay, then your image should be, your filter should be K by R. Otherwise you can't do inner products. See, you take a K by R cube and put it into a subsection of P by Q by R cube, and then you take an inner product. That will give you one number, because after all it's an inner product that we are doing, right? Is it okay? Now suppose we have P is already taken. L, okay, we'll do L. Okay, let's say that all of them have k by k by k into R as size, and we have L filters. Okay, then we are doing convolution. What will we get? We get, here we'll get, this will be P minus k, Q minus k plus 1. I mean, I'm assuming that this stride size is k, right, or divided by s. Okay, maybe we can do that. This will be divided by s. If the stride size is s, where s is the stride size. Huh? P minus k by s plus 1. Yeah, that's what it is. And there will also be a floor here, no? This may not be an integer, so will it be a two-dimensional grid? Yeah, there will be another dimension to this. Okay, come here. Now this will be so the number of channels in a subsequent layer will be equal to the number of filters in the previous layer. You got that? Now suppose I go deeper. The third dimension of the filter in the next layer has to be equal to the number of filters that we have chosen in the previous layer. Huh? R will not come, no? Because you are taking this k by r, taking inner product, so that will go away. You are actually marginalizing along that dimension, so r will not come. Is that all right? Now, what are the hyperparameters here? Hyperparameters are
Filter is equivalent to neuron.
filter is weights. The inner product that you take is, see, a neuron is implicit, right? I mean, because it's a mathematical operation that we are doing. So a neuron is implicit. This entire operation is a neuron to me, isn't it? Inner product, and then you take that sigma nonlinearity is what a neuron is. Okay, so hyperparameters are number of filters in each layer and filter size. Can there be different sizes of filters in each layer? Yes, Inception Net does that. I'll take a few names. Okay, you make different choices for these hyperparameters and name that CNN with your name. That's what people have done, or your company's name, or whatever, or whatever fancy name that you want to name it after. Filter size, and what else? Stride. Of course, if you have stride, and you need to do padding also. Who is asking? Okay, stride is, I told you, I'll just tell you again. See, when you place your filter on your image, right here, it's the k by k pixels that you cover, or what should be the next operation? The next operation should be take another k by k subset of data and then do inner product. Which k by k do you take? Do you take overlapped one or non-overlapped one? How many data dimensions do you stride over? I mean, if you overlap, if stride size is 1, then you overlap by k minus s stride, this thing. If it's k, then you don't overlap, and so on. Yeah. And what else? So you have a number of layers also. Huh? That is number of filters, no? Number of neurons in each layer here is number of filters, isn't it? No, number you choose. That also you choose. No. Oh, layers meaning depth. So layers in a neural network is the depth of the neural network. See, that's why I didn't want to take that letter L here. What is the depth of the neural network that you talk about? Okay, you might have heard about these architectures, ResNet and all that, right? ResNet 64, ResNet 128. That 128/64 talks is actually the depth of the neural network. How many layers that you have in the neural network? Okay, so almost done with CNNs. A couple of more nuances before we go there. Any questions? Correct, correct. Stacking the result of every filter as a channel, right, in the next layer. So this becomes the input to the next subsequent layer and so on. So always this is the rule, right? For a CNN to work, you'll have to ensure that the third dimension of the filter, okay, is equal to the third dimension of the input that you are looking at. Otherwise, inner products don't work out. No, dimensions have to match. That's it.
So having a little difficulty understanding why the ERM will converge to different weights in every layer.
Okay, it's the question is, why would ERM ensure that the weights in each filters are different? Okay, there's no guarantee. So the question is equivalent to asking in an MLP, why would every weight be different? It's exactly the same question. There is no guarantee. Right? We are just having these many parameters that the neural network can choose from. It will choose. Empirically, what has been observed though is that if you have, let's say, some 10 filters, they have seen that one filter responds to edges, the other filter responds to color, and so on. Is what empirically has been observed. Why would ERM ensure this? There's absolutely no guarantee that ERM will do this. It's simply a function, and we have gradient descent and optimization that we are doing on a loss landscape. That's all. So, I mean, the question is same like asking, suppose I have a 5 parameter model, simple polynomial, right? I do gradient descent on it. What is the guarantee that all coefficients will be different? There is no guarantee. However, since ERM is there and the objective is to minimize the empirical risk or the average loss, if you choose all of them to be the same, the chances of minimizing the training error will be low, isn't it? Go back to the same polynomial question. Suppose I have the data coming from a 5th degree polynomial which is perturbed with some noise, and my model I choose my model to be a 5 parameter or a 5th degree polynomial. If all of my parameters will be the same, will the training error converge? It won't. However, suppose my data is coming from let's say 2nd degree polynomial and I am using a 10th degree polynomial as my model, which is an over parameterized model. Will some of my coefficients be 0? Of course we will be, and we will enforce that they are 0 by regularizing, isn't it? That's the whole idea of regularization. Now, the assumption is that typically we under parameterize the models, right? Or rather, even if you over parameterize, we regularize to ensure that that we trade the bias variance. See, everything that we did with bias variance decomposition still holds. Even if you are using a CNN, you still have the training error, test error, and you have the bias variance decomposition, and you will have to choose the best point. Yeah, but short answer, theoretically there is no guarantee that these will be different. It's just optimization.
The stacking of the multiple filters which we have, as we go through the layers, they kind of shrink, right? Because they are actually
Come again?
the feature maps which we obtain in each layer, they are communicating with each other in the every next layer. So the kind of stacking will reduce it. It's not kind of parallel. Comparing this.
Didn't get the question.
Comparing this with the MLP.
Uh,
So let's say if we consider each filter as one MLP altogether with parameter sharing and everything. But in the next layer itself, all these features obtained from different neural networks communicate with each other.
Sure.
So the kind of stacking is not parallel, right?
Still didn't get the question. Maybe we'll take it after the class. Yeah. Um, Anything else? Okay. So suppose you are solving a classification problem, right? Which is an image classification problem or something. So how is it done typically? I'll just give you examples of neural networks. Okay. So before we go to the examples, maybe as I said, there are a couple of other things that people do. Something called pooling. There's something called pooling operation. Okay, let's say that we have an image of size or a data of size p by q. Okay, then I want this to be reduced by half. For whatever reason, there is one reason could be that that so sometimes what happens is if there is a lot of noise in the image, as they say, you need to smooth out the image or the pixels. In the sense that there are some noise that are added in the or comes up in the image, and to get the features to be extracted in a particular way, then you have to smooth it out. Low pass filtering operation. Okay, what is low pass filtering in image processing community? It is subsampling. And so what you do is, if you want to reduce the image by 2, replace every pixel in the input with the average of the neighboring pixels and reduce the size by half. What I'm saying? This is average pooling, right? Where you reduce the size of the neural network or the input data or activation map by 2 by taking an average. If you take 4 by 4 grid, right, and then take an average, then what? Then nothing. Yeah. So but these kinds of operations can be looked into as hard coded filters. For instance, yeah, this is what I wanted to say. If you take a 2 by 2 filter with all ones and take an inner product, it is equivalent to taking an average, no? Of course, you need to divide by not all ones. It will be 1 by 4, 1 by 4, 1 by 4. If you take all values to be 1 by 4, then doing a convolution with such a fixed filter with values 1 by 4 is equivalent to doing a 4 by 4 averaging. This operation is called pooling. What did I say? 1 by 4 is the value. The filters are 2 by 2, 2 by 2, and did I say 4 by 4? Yeah. So then it is averaging 16 pixels. Yeah. You got the idea. The 2 by 2 filters, and then this operation is called pooling. Okay. This is fixed convolution.
Assuming that the information is not much close.
Information is, yes. I am just saying this as an addendum because I am not a big fan of pooling layers. Because I still sort of don't understand why one needs pooling layers. It's just to reduce the dimensionality, reduce the size, and so on. So that's how people do it. This is average pooling. Okay. There's also something called max pooling. If you do max pooling, then you take a 4 by 4 grid and replace it with the maximum value of that. That's max pooling. Okay. Now that's a non-differentiable operation. How do you do backprop? If you do max pooling, you'll have to hard code. It's not exact. See, if you take a 4-dimensional vector or 4 numbers and replace that with the max of those 4, it's a non-differentiable operation. How do you, when you come back, what value do you replace with which? They'll just do some approximation and do it. There are multiple ways of approximating backprop in differentiation in maximum operation. For instance, replace all of the pixels by the same value and so on. That's one bad approximation that is done. So this is called max pooling and average pooling and so on. Okay. Now, yeah, so this sort of completes how CNNs are built. So CNNs end to end will look like this. Didn't expect this thing to take so much time. Okay, so we will start with let's say that suppose we have we will say examples examples of CNN for end-to-end tasks. Okay, let's first take the classification slash regression tasks, or let's say classification tasks. So you start with a PQR grid. This is the image. So then you have conv layers, and then pool, conv, pool, conv, and so on. You keep doing it, and after that you do what is called as flattening, which is simply raster scan of the grid that you have and make it a vector of k dimensions. Okay, and then you have an MLP. This is k classes at the end, and then do ERM. That's it. This is how you solve classification problems using CNNs.
So there is a feed forward afterwards, basically. After
You have to know, because finally you need a k dimensional one hot vector, right? After the final convolutional layer, you need to all flatten all of them, meaning arrange them into a vector and then do a fully connected layer, which is an MLP. Yeah, because you have arranged that as a grid. Keep getting grids. After the grid, you simply flatten. And by the way, there is no sacrosanct sanctity on writing con after pool after con after pool. You can do con, then pool con. It's a complete design choice. Right? There is no reason why they should be alternated. Just given an example of. That's why I wrote an example. So this is for classification. Is that okay? Now, you might have heard of things like AlexNet, LeeNet, ResNet, InceptionNet. All of them are examples for this, with hundreds of layers. In residual neural network, right, there is one other kind of connection that is called the skip connection, where simply what is done is you connect the neuron from the previous layer to the next layer, right? It's just skip one. The idea is that, and that you do with an identity operation by assuming that you have a path to learn identity. So that's the motivation that is given, right? So examples are, so LeeNet. So this LeeNet is named after that Jan LeCun guy. There is AlexNet, and there is ResNet and all that, InceptionNet and whatnot. And please look into some of these examples, right? They're simply convolution layers. And in InceptionNet, what they do is, this was I think Google's paper, where they said we will have filters of different dimensions in each layer. So there were 9 by 9, 7 by 7, 5 by 5 filters, 3 by 3 filters in the same layer, concatenate and then do different kinds of, when they play with these hyperparameters, right? This is for classification, right? So let's look at, of course you can do the regression tasks also here. Okay. Now what is the example of a regression task in image processing? So given an image, what do you want to regress over? See, one classical example is that of bounding box extraction, where suppose you are given an image and you want to find out, put a box around a particular object. One example is tumor marking. So you are looking at images with some particular type of abnormality and you need to do a bounding box detection. The way it is done is, cast it as a regression problem where the output will be the coordinates of this particular rectangle. You need 4 numbers to represent a rectangle, isn't it? So give those 4 numbers, your x will be an image, y will be those 4 numbers, regress like this, that's it. Okay, this is one example. The other example is what is called as a fully convoluted network, whatever. Fully convolutional. See, I am not a big fan of architectures because they are like Lego blocks. It's left to one's imagination. One can do whatever they want by doing this. There are some examples, that's it. So the example for this task is, let's say, what is it called? semantic segmentation, yeah, okay, let's say. So semantic segmentation, what is the task? Given an image, you need to classify each pixel, okay, as belonging to one of k classes. Let's say that you know that there can be 100 types of object categories in your image, okay. Now given an image, the output has to be another image, okay, that will have different colors for different object categories. So input is an image, output is an image. So that's an example of fully convolutional neural network. The other example can be what people call as tile transfer, where you give your picture and the output has to be the cartoonized version of you. Input is an image, output is an image. Okay, these kinds of applications. So how do you do that? Start with P by Q by R image and then keep doing this conpool business and do it. Finally, don't flatten it, okay. So you'll have to ensure that this will be P by Q. Suppose you have, let's say, k object categories. The number of channels here would be k, because there will be every slice corresponds to an absence or a presence of that particular object. This is called the segmentation map. In these kinds of applications, typically what happens is the architecture of the neural network. See, generally for classification, what happens is as you keep moving deeper and deeper into the neural network, the sizes of the grid will keep reducing, right? Because P by Q by R is much larger compared to number of classes, k classes. Therefore, you need to reduce the size. But in a fully convolutional setting, right, what is done is that you start with a P by Q image, right, and then you keep reducing the size, okay, up to a particular point, and then from there you keep increasing the size back again, because what you need is the output to be of the exact same size as the input, isn't it? Right. So therefore you first reduce the size and then create a bottleneck and increase the size. Now how do you increase the size in a convolutional operation? In an MLP it's okay, you increase the number of neurons, but in a convolutional setting, how do you increase the size? Yeah, see, if you change the filter size, this operation is called transpose convolution. Same thing, but instead of convolving with the filter, you transpose it and then convolve. From the signal processing community, it is equivalent to the upsampling operation. People also do fixed upsampling. So you can learn the filters okay. By the way, this architecture is also called the encoder decoder architecture. Encode the information and then decode it. Okay. Yeah. This has a name in the computer vision community. This is called U-net, because the shape of it looks like a U. See, I am rushing through all this because this is not a computer vision course, right? But I am just giving you an example of how convolutions can be used. Okay, is that all right? Now, how do you learn backprop ERM? That we have learned. The only thing that is to be ensured is that when you do that, you will have to ensure that the parameter sharing and the local receptive field are encoded into your forward equations and backward equations. Please take that as a homework and do it. It will be a part of your assignment anyway. I'll ask you to implement a convolutional neural network from only using NumPy. Yeah, but I think will be done in tutorials, but you'll have to ensure. Same thing goes with any architectural tweak that would be done. I thought I would finish both CNNs and RNNs today in one class. Okay, yeah, this is about CNN, so we will stop the discussion on CNNs here. And next class we will look at the other kind of topology, which is called the sequential data, for which another kind of regularizer is imposed on the MLP, and that is called a recurrent neural network or an RNN. We will look at that the next time we meet. Okay? Thank you. That's all for this today's class.